The day-to-day, I will post a sheet that lists the topics, the scope of the exam, and just a brief review of the concepts. So you can use that as to launch your study guide, if you will. So keep an eye out for that. I'll post that today. And then, we'll just proceed with the finite element lectures today. We'll probably get most of the way through the truss lecture, and then on Monday we'll finish that up. And we may have some time to spare on Monday, so either, depending on how much time we have to spare on Monday, I'll either use that to see what questions you have on the exam and maybe dedicate some of that time to reviewing concepts for the exam, or maybe, again, depending on how much time and how the flow is going, maybe we'll start talking about visual analysis in that Monday's lecture and then save exam review talk for Wednesday next week. So that's what I'm looking at next week. Any questions about the exam or anything coming up? Okay. All right, good deal. As a reminder, you are allowed to have one note sheet for the exam, both sides of a 8.5 by 11 handwritten. So my only request is that it's handwritten by you. It's totally fine if you want to write it on your tablet and then, print it. It just needs to be in your handwriting, right? So, all right. So we finished up last time talking about applying the concept of finite element analysis to a basic linear spring. And this is a common way of introducing the topic. A lot of textbooks start with this as well. And as I mentioned, right, moving forward, we're not actually going to be looking at problems that have springs and spring stiffnesses, K1, K2. We're going to be dealing with structures which have their own stiffness associated. That's tied to, remember, material properties and geometric properties. So the next example demonstrates that, right? And it's identical to the example we looked at before, where we're going to see two elements, right, each with their own stiffness value. And it's going to be fixed at the left end with an applied force in the positive direction on the right end. So we'll see how the process just looks a little bit different, or I should say the process is the same. We'll just see how, right, the results look a little different because we're now in terms of axial bar specific behavior, right? So here we have, again, these two elements, right? Two different AE values, all right? So the product of A and E for element 2 is 2 AE relative to the product of the stiffness and cross-section area for the first element, right? So you have 3 AE over L and 2 AE over L representing your stiffness for those two elements. The boundary conditions are the same, right? So what we know and don't know at each node. Node 1 is fixed, so it's not going to displace at all. Nodes 2 and 3 are both free to move along the axis, right? So those two displacements are unknown. And remember, at each node, you know exactly one thing associated with the degree of freedom. So where we don't know those two displacements, delta 2 and delta 3, that means we must know the external force associated with that node. At node 2, there is no applied force, so F2 is equal to 0. At node 3, that applied force is given as positive P. And of course, we don't know the reaction force at the support, right? So our matrix representation looks a little bit different from the spring stiffness example before, right? Because we just don't have the K1 and K2 terms. We're plugging in 3AE over L and 2AE over L instead. We can bring that AE over L out in front of the matrix, and so now we have a nice coefficient matrix with just numbers in them. This makes it a lot easier to solve. It's more user-friendly. Process, again, is the same. We will eliminate that first column, all right? So get our blue color back. All right, so since delta 1 is equal to 0, that means the first column in our stiffness matrix is going to be multiplied by 0. So those values are not going to give us any information in this solution. We can just eliminate that column altogether. Then, when we take our first partition, which will be the rows that have known forces, right? So that would be rows 2 and 3. We now have 2 rows, and with only 2 columns left in our analysis, we have a square matrix for our first partition that we can invert and then solve for those unknown displacements. So we take our first partition. Notice, all right, I did want to point this out. So the overlay, right, occurs at the common node. We talked about that last time. So node 2 is the node that connects the 2 different elements together. So the stiffness values will be added together in our stiffness matrix for the 2 elements, right? So we have the 3 plus 2 at the overlay. I'll just highlight that as our overlay. So that is where that 5 comes from. Then taking the inverse of that stiffness matrix, pre-multiplying both sides of the equation, we solve for the unknown displacements. So we have delta 2 and delta 3 now in terms of the applied load, P, and in terms of the stiffness, right? Now that we know those previously unknown displacements, we can then go back to the first equation, right, and solve for F1. So technically in the second partition, right, you can use this first column if you want to, but again, this value is just going to be multiplied by 0, so it's just extra work, extra stuff to write down. So I recommend just sticking with the same 2 columns that we used for the first partition. Don't try to, what I will say is, don't make the mistake. It's common to try and say, oh, well, I used these 2 columns for the first partition. That means I have to use the columns that I didn't use in the first partition for the second partition, because that's what we're doing with the rows, right? But that's a mistake. Not only will it not be a compatible matrix dimension for your math to work out, but again, this column is just not going to give us any good information. So if you want to include it in your solution for the second partition, again, that's okay, but make sure you are using those 2 columns that are associated with the displacements that are not 0, right? So then plugging in our delta 2, delta 3 values in our second partition equation, solve for F1, get that it is equal to negative P. Of course, that checks out with equilibrium, right? So a lot more friendly to work with axial bar system compared to spring stiffness values. Of course, if you had numbers to plug in, this wouldn't be bad, right? But it's just a little bit more of a headache to write it all out in terms of K1, K2. All right, any questions? All right. So one thing I will just note down here, all right, I said it, but it's worth making a note, that the results, all right, specifically the displacement results, are in terms of the applied load and the stiffness. All right, so now we'll just do a quick recap of this whole process as we have covered it so far in the context of single-axis axial force systems. Number of degrees of freedom, right, is 1, and that is along the axis. At each node, we know exactly one thing, either the force or the displacement. size of the stiffness matrix for one element will be 2 by 2. Or I'll say each element, right, for each element. And then when we overlay those element stiffness matrices, we'll get the size of our overlaid matrix for the whole system. And that's going to be 2n by 2n, where n is the number of nodes. All right, so it's another common mistake to say, oh, I have 3 elements, so my stiffness matrix is going to be 2 by 2 for each element, so that's going to be a 6 by 6 stiffness matrix, but that's not correct. Because if you have 3 elements, maybe you have 4 nodes, right? So you got to think about that. And actually, let's see. So actually, my notes were wrong. For a single axis axial force system, right, I was getting ahead of myself. For a single axis axial force system, it is n by n for the system overlay, right? So if you have 3 elements, 4 nodes, you'll end up with a 4 by 4 system matrix rather than a 6 by 6 if you were gonna just count up how many elements you have and multiply that by 2. I'll correct that in my notes. There we go. All right. So then a quick recap of the overall procedure, right? I'm going to label the first step 0 because sometimes this is already done, but you want to make sure that the nodes are numbered if they aren't already. And we're going to follow the rule in this class that nodes should be numbered left to right. With trusses and frames, it can get a little bit tricky with that rule, but in general, let's just try to move left to right through the system if you have to decide on the numbering of the nodes. Then you want to define the element stiffness matrices. And you want to normalize them. We didn't really demonstrate that yet. I'll point that out in the next examples that we'll look through. Then you want to assemble the overlay. All right, so that will be your n by n. Apply boundary conditions. Partition. All right, and then first partition will solve for the unknown displacements. And the second partition will solve for the unknown forces. And then last, sum of forces in the x direction to verify that equilibrium is satisfied. So the single axis axial force system is unique in that it is the only time that you only need to use one equation of equilibrium to verify that equilibrium is satisfied, right? Because sum of forces in y doesn't really apply, and sum of moments about a point really doesn't matter either in this scenario because since we only have motion along the axis, there's really no risk for rigid body rotation, so we don't have to worry about that. But that's the only time we only have to use one. And it's the only time that we don't have to check sum of moments about a point. All right, questions so far? All right.
Sorry, could you state again why we only have to analyze the forces in the x direction?
Because it's just that's the only way that the structure can deform or move, right? It's a single axis axial force system, single degree of freedom. So
Gotcha.
There's no risk for rigid body rotation, no risk for movement in the y direction, right? It's just along the axis.
Okay, thank
Yeah.
you.
All right, so now we'll look at a couple other examples. So here's a 3-element example. All right, you have 4 nodes. So we can expect the overlaid matrix to be 4 by 4. So I'll just say this is a 1 degree of freedom system times the number of nodes, which is 4. Gives you the size of the overlay. So 2 elements, right, have the same stiffness value here, and the element in the middle has a different stiffness value. We've got a fixed support at node 1. Nodes 2, 3, and 4 are all free to move, and we have an applied load at node 2 and another applied load at node 4. So establishing what we know and don't know at each node, again, for this single degree of freedom system, you know exactly one thing per node. So at node 1, we know the displacement is 0 because it's a fixed support. At node 2, we don't know the displacement because it's free to move. We do know the external force, right? It is P in the positive direction. At node 3, we don't know the displacement there, so we do know the external force. Since there's no applied force there, F3 is equal to 0. At node 4, again, we don't know the displacement. We do know the applied load. So then this step is showing you writing out the individual element stiffness matrix equations, right? So for each element, you have your AE over L value out front of the 2 by 2 that consists of 1s, right? And negative 1s. And since one element has a different stiffness value out front, this is where that normalize the stiffness matrices comes into play. All right, we want to, before we add these 3 together, we want to make sure that we have the same value out in front of the matrix, all right, so we can do that. So I'm just going to take the constant in front and put it into the matrix so that we've got all of our numbers together and then just AE over L out front. So that's where we get the 2s and the 3s that we will then add together. So we ultimately end up with AE over L in front. Now, I did note up here in the first matrix that we have delta 1 is equal to 0, right? But I don't want to eliminate that column just yet. Wait until you've done the overlay to eliminate columns from your matrix. Now that we have the overlay, right, a 4 by 4, we can eliminate that first column, right, since it's going to be multiplied by 0. Get rid of it. And then our solution will start with the first partition, the rows that have known forces. So those will be the last 3 rows. First partition then is going to be this chunk right here. The overlay occurs on the diagonal terms, right? So Node 4 doesn't connect to elements, right? But nodes 2 and 3 do. So this is where you have the overlay. In the second column and second row, and a third column and third row, right? All right, so then taking that first partition, right? Find the inverse of that stiffness matrix. You can use your calculator, Excel, whatever for homework. Pre-multiply both sides and write the solution of the unknown displacements in terms of P, L, A, and E. Then, knowing those displacements, plug them in to the second partition equation, right, and solve for the unknown force, F1. From here, we find that F1 is equal to negative 2P. That checks out with equilibrium, right? Sum of forces in X is equal to 0. So again, even though we all probably knew that immediately just by looking at the problem, we did not use that information in our solution, right? We just used it to check our solution. So that's important. Yes?
How do you get those like 1, -1, -1, matrices at the beginning? Is that just always like that?
Yeah, so that's what we derived last time using the concept of a spring, right? So we ended up with this form, and then down here showed that with an axial bar element, this is the general equation for an axial stiffness,
Okay.
single axis axial stiffness. Yeah. Now, in your homework, I'd like to see for these types of problems, axial force systems, I would like to see you writing out the individual element matrices as shown in this example. Write out the overlay, show the first partition, and show the inverse, right, in your work. You don't have to show how you calculated it, right? Do that in a calculator, Excel, or something. But at least write down what it is. And then, show the equation that you use to calculate the results of each partition, right? And then produce those partition results. So I think in your homework, once a problem like this is assigned, you'll also be requested to draw a final free body diagram and just verify that equilibrium is satisfied. So in this example, I didn't draw a free body diagram to summarize, but that would just be adding the 2P load to what's already given, right? So that's going to be a lot more important when we get to beams and frames, and trusses. But just as a heads up, that's always something that you'll want to do in your summary of results. All right, so next example, we have a system that has more than 2 elements sharing one node. So this is also an indeterminate system because we have 2 nodes that are fixed, right? And notice what happens here, right? So we start off, we have, again, 4 nodes, right? So K will be 4 by 4 because it's still a single degree of freedom system. Breaking down what we know and don't know at each node. At node 1, fixed support. We know delta 1 is 0. That means we don't know the reaction force. At node 2, again, fixed support. Delta 2 is 0. Don't know the reaction. At node 3, right, there's this rigid element that is attaching all 3 elements at the same point, right? And since this is an single axis axial force system, again, we don't have to worry about any rigid body rotation or vertical translation. And so however much element 3,4 moves at node 3, element 2,3 and 1,3 will move the same amount at that point, right? So delta 3 will be the same for all 3 elements. We don't know what that delta 3 will be, though, because it's not restricted from moving. We do know that there's no force applied at node 3, so F3 is 0. And then F4 is where the force is applied. So we know that. We don't know the displacement of node 4. Setting up the individual element matrices. Here we have for element 1, 3, right? Stiffness, since they all have the same AE product, the stiffness values will vary according to length, right? So for the first element, 1, 3, we have AE over 2L. So I just brought the 2 inside, right? So just lumped the normalization into one step. We want to make sure we have AE over L the same in front before we add them together. And then for element 2, 3, right, has value of 1L for length. So that's going to be a matrix of 1s. And element 3, 4 will be the same stiffness, have the same stiffness matrix as element 1, 3, just different displacements and forces associated with it. So then the overlay will occur at node 3, all right? So in the overlaid matrix, we want to focus on the third row and the third column because that's where all the elements come together. And that's where we sum the values from the third row and the third column of the individual element matrices. So I'll note here, then the first partition, right, again, after eliminating the columns that will be multiplied by 0, which is delta 1 and delta 2, our first partition will be using the rows with known forces. So we'll have this chunk right here as our first partition. It's smaller, right? Smaller than the previous example, which had the same number of nodes, same number of elements, right? But because this is indeterminate and we know more displacements now, we rule out more columns in our overlay, so that shrinks the size of our first partition. Easier to solve, right? If you wanted to, you could do this without a calculator. And we get our delta 3, delta 4, plug that solution into the second partition, which again goes back to the overlaid matrix, and we'll use rows 1 and 2. All right, so technically you could include all 4 columns in the second partition. Can't do that for the first one, but can for the second. However, it's more convenient to just forget about the first 2 columns since they're going to be multiplied by 0 anyway. So then solving for those unknown forces, we get negative 1/3 P and negative 2/3 P respectively at nodes 1 and 2. Now, equilibrium equation checks out, right? And everybody's happy. Any questions? Yes?
How do you put the initial 3 matrices into the overlay matrix? I'm a little confused on how that.
Sure. So you want to map, once you label or identify the rows and columns that are associated with, node 1, node 2, node 3, node 4, forces are the rows. Columns are associated with the displacements, right? Node 1, 2, 3, 4. So I recommend keeping them in order for simplicity. You don't have to, but I highly, highly recommend that. Then you identify, right, the value from the node 1 column and row from each element and place that in the corresponding node 1 row 1 or node 1 column and row in the overlay, right? So here, right, for all of these, I highlighted the node 3 columns and rows in every element matrix. So all of these values will go into the same position in the overlay. That's where they get added together. But if we wanted to look at, like, here's the node 3 value of displacement and the node 2 value for force, all right? So this is going to go in the node 3 column and the node 2 row in your overlay. Yeah, so I highly recommend labeling your columns like I do according to the node that it's associated with. That will help you to map those values. A lot of times it can be simplified. So in the previous example, right, we didn't have any nodes that connected more than 2 elements, right? So if you have a system like this where it's a beam with elements or an axial force system with just, one element in between 2 nodes, then you can really just take your matrices and drop them one over the other like that. All right, so this would be the first matrix, here's the second matrix, and then the third matrix goes here. And then the values that overlap at the diagonals will be added together. But if you have a scenario like this where you have a node that connects more than one element, it's not that straightforward. And when we get into trusses, it will be also a little bit more complex. So mapping it is highly, highly recommended. Yeah. Great question. Any others? Yeah.
When you did the inverse of K, where'd you get the 4/3?
So that is coming from the determinant, all right? So if you take the determinant, which is, remember, the difference between the cross products, and then the determinant goes in the denominator of the inverse, right? So the determinant would be 3/4 in this case. Yeah. Any other questions? All right. Very good. So let's see. Yeah, we're right on target. Now we're in week 6 here. We already talked about what's coming up, so I'm going to skip through and go on to trusses. Now that we've talked about how to apply finite element method to a single axis axial force system, now we're going to build on that and start thinking about trusses. Remember, trusses are just assembly of individual single-axis axial force systems, right? We called them 2 force members earlier. So we're just going to really be starting similarly to what we did before, right? We'll write individual element stiffness matrix equations for each element in terms of their local coordinates. Then we have to transform them. So I'm going to demonstrate that process as it applies generally, and then we'll get to a shortcut equation that you can use so you don't have to do the transformation, the whole transformation process every single time, right? We'll just have a formula that you can use to get the transformation. And then, so that's going to lead us to talking about global and local coordinates, coordinate transformation. With trusses, all right, so because, again, it's a system where individual members have different orientations, different local axes, we have that global system to use. We're always going to be solving for global results first. So that will be in terms of your Cartesian X and Y displacements. Once we have those global solutions, then we can go back to our local relationships and solve for internal member forces. That's your tension, compression for each member. And we can solve for the axial deformations of each member as well. So we'll look at that whole process. In your textbook, the sections to read are 19.6. I'll put 19.9 in parentheses. It would be helpful, but maybe not essential to read that one. And 19.10. Let's see. Is this the next page in your notes for you, the summary page? It is? Okay. So that is meant to go at the end of our truss lecture. So save that one for later. We'll come back to it. Let's see, I'll stick it here. All right, so we're gonna start with this generic truss, and globally, all right, again, we have the traditional Cartesian XY. Because we have to represent two directions of displacement for a truss, that means that we have 2 degrees of freedom. All right, we talked about this a bit in the intro to FEA the other day. So our 2 degrees of freedom for trusses are the global X and global Y components of axial displacements and forces. I'm going to shorten it, all right? Axial delta F. Locally, all right, each element is still 1 degree of freedom. Right, which is along the axis. And specifically now we have to think about where we place the origin. The origin will be at the lower numbered node. Now locally, all right, I already alluded to this, but locally, the displacements and forces that we're solving for are the axial displacements or deformations and the internal axial forces, tension or compression. If we consider a local element, this one in particular labeled IJ, we place that origin at the lower numbered node, all right? So X will be positive from the lower numbered node to the higher numbered node. And then we have our axial displacements and forces noted at each node, right? Our local stiffness equation is written here. So this is just exactly what we were looking at in the previous lecture. And that's, again, just for one element. Now, our goal here is to relate these global, let's see, how do I want to say this? Right now we have our local stiffness equation, right, which just relates the local forces to the local displacements. What we want is an equation that will relate the global forces to the global displacements for this element. So I'm going to write that down. All right, so this is just the previous equation in matrix form. Notice that the matrix dimensions are pointed out here, and you can verify that they are compatible, right? So the inside dimensions have to match. The outside dimensions give you the dimensions of the product, right? Now, our local to global relationship is just defined by geometry, all right? So we have to make sure that we define theta consistently. So theta is always going to be measured positive counterclockwise at the lower numbered node from global to local. So here, the global axis, right? Versus the local axis, which is along the length measured from node I, gives us our angle theta, and the positive direction is counterclockwise. So we can relate then our local deformations and forces in terms of global components. So that's noted on the figure here. We have our X and Y global components of X at node I, all right, the deformation at node I. So we'll look at that one and break it down. And the notation here is such that the G represents global, and then the odd numbers represent the global X direction, the even numbers represent the global Y direction. It's not my favorite numbering system, but it's one that you may see. You're welcome to use a different one. I'll demonstrate a different one on the next page as well. So the global X component of the axial deformation at node 1 is going to be xi times cosine of theta. All right, so we can all see that pretty readily. Similarly, the global Y displacement at node I will be xi sine theta. All right, so that's also pretty evident. The next step uses a trig identity. All right, so this is using a math trick, if you will. We're going to say that xi is equal to xi times cosine squared of theta plus sine squared of theta. All right, you all remember that identity equals 1. So applying that trick, right, and then plugging in these items, we can say that xi is equal to x1g times cosine theta plus x2g times sine of theta. And then this equation is what we have up here. We can do the same thing at node J. So this is how we get this relationship, because looking at this right here is not immediately obvious from the diagram, but applying this neat math trick, we can get there. The reason we want that form of the equation is for convenience in our solution, right? So it gives us this transformation matrix here, which we call beta. So this equation is just rewriting these two equations in matrix form. All right, so that is the transformation matrix defined below. And so this represents our second step in the transformation process, which is transforming the displacements. We still haven't addressed the forces yet. We still need to do that. But now we have the local displacements in terms of the global displacements, which is what we ultimately need in order to reach our goal of relating global forces to global displacements. So now applying it to forces, this is a little bit more straightforward. Here, we're just simply going to write our global forces in terms of local forces. All right, so we have F1g equals Fi cosine theta, F2g equals Fi sine theta, etc. And then we're just going to use those forms of the relationship directly to obtain an expression that relates the global forces in terms of the local forces. So you'll notice then that this matrix is the transpose of the transformation matrix that we defined for the displacements, right? So that's nice and convenient as well. Another notation that you may see to indicate transpose can be the prime, right? So just in case you encounter that, that's sometimes used. I think the T is more common. And that's what the T is what I default to. So, all right, so now we have this third equation, right, that transforms our forces. Now we can start making substitutions, all right? So we have our global forces equal to beta transpose times local forces. We can plug in, all right, for our local forces, our first equation, F equals kx. That gives us this equation right here, all right? So plugging in kx for F. From there, we have our now local displacements are showing up. So we'll say, I'll use a different color. We'll say, now we're going to plug in our second equation. All right, so that's x equals beta times xg. After doing that, we now have our global forces in terms of our global displacements, all right? With a little bit of simplification here, so this beta transpose k times beta is substituted with kg. All right, so we define that below. Now we have a global element stiffness equation. We have reached our goal. So, expanding this, all right, remember those betas include a bunch of sines and cosines in them. So if we expand this equation for kg, this is what it looks like, all right? Who wants to write that out over and over again? Not me. So we'll simplify it with this shortcut by saying A is equal to cosine beta, B is equal to sine theta, and then you have a formula to calculate your global stiffness matrix equation directly. All you need to know is the angle theta, all right, and the individual, or I guess, yeah, all you need to know is the angle theta and then whatever AE over L value you may have. So then our, let's see, I'll break this down. So we've got, this is your beta transpose, right? This is your local element stiffness equation, and this is beta. So this equation down below, right at the bottom of the page, can be your starting point for a single element. So that's the good news. You do not have to go through this whole process for every element. You can just skip straight to this equation and then relate your global forces to the global displacements. Later, we may want to go back to some of these equations that we used, all right, to calculate the local forces and displacements. We'll talk about that on Monday. Any questions? All right, I know it seems a bit overwhelming. Once on Monday, we'll recap this process and then apply it to some examples, and then it'll start to make more sense. All right.
Where does material stop for our test?
It's through lecture 11, I think is what I wrote. Yeah, so through lecture 11, elastic curve. So homework 4, up through homework 4. Yeah.
Will there be like a review sheet or practice test, kind of like we have in dynamics?
So I don't have practice tests, but I will be posting a review sheet by the end of the day today. Yeah. Yeah. All right. Good deal. Have a great weekend. Yeah.
Are we gonna have homework next week? Just in terms of like
Homework
knowing what-
due.